After learning about RocksDB, which is closely related to TiKV's database persistence, let's take a look at another feature of TiKV, distributed transactions. If we want to manipulate multiple rows of data at the same time, and these data are in different regions and possibly even on different TiKV nodes, we need distributed transactions to ensure consistency of operations. TiDB uses Google's Percolator model and uses two-phase commits to provide distributed transaction support. Let's take a look at an example. The entire database needs to have a globally unique and monotonically incrementing timestamp that identifies the start time of the transaction and a commit timestamp which documents when the transaction was made permanent in the database. The timestamps are provided by the PD. Next, Percolator uses the three column families in the RocksDB instance to store data, transaction, and lock information. You can see these on the diagram. These are default, lock, and write. This is best described using an example. Take a look at the left-hand side of the diagram. We see a transaction where we are changing the value of key 3 from XXX to franc. So we write 3 and franc in the default column family. Then we will record a lock with key equal 3 in the lock column family. TiDB server then puts the values 3 and franc in the write column family, and if this transaction is committed successfully, that is written to disk, it will be recorded in the write column family and the corresponding lock entry will be deleted. This is a continuation of the previous slide. Think of it as column family trivia. So the write column family. When a user writes a row of data, if the length of the row is less than 255 bytes, it is stored in the write column family. Otherwise, the row is stored in the default column family. Default column family, used to store data greater than 255 bytes in length. Here's our transaction. We have a begin and a commit, and in between we're setting key 1 from Tom to Jack and key 2 from Andy to Candy. Assume that key equal 1 and key equal 2 are in different TiKV regions. Also, notice that they are on different TiKV nodes. Key 1 is on TiKV node 1 and key 2 is on TiKV node 2. First, at the beginning of the transaction, we get a start timestamp from the PD. Assume it's 100. We enter the first stage of Percolator, pre-write. At this time, since there's no commit, we need to write the two column families, lock and default. As you can see from the figure, we are writing when entering default. We added a timestamp to the key, and the values of the two modify lock column families are not quite the same, mainly including lock types and start timestamp. There is an important point here, that is, modify key equal 1 and key equal 2 in the transaction. In the lock column family, we only use the first modify, that is key equal 1 as the primary key, and the lock with key equal 2 points to key equal 1, that is the value in the lock column family. At the same time, we also notice that in the default column family, where data is either modified or deleted, there is a new insertion key value pair rather than a modify or deleting the stored key. This will be explained later in the introduction to MVCC technology. Second, let's go to the second stage commit of Percolator. At this time, we'll get commit TS from the PD and assume it's 110, and it will be written into the write column family, key plus timestamp, and the value of the start timestamp of this transaction. The primary key was deleted in the lock column family record. After the commit phase is complete, when we want to read the data, we will find out whether key equal 1 or key equal 2 was committed. We only need to determine if there was a lock in the corresponding lock column family. If there is no lock, or if the lock is deleted, that is marked D, we can read it, otherwise the read will fail. Finally, we found that during commit phase of Percolator, we only had to delete a primary key with key equal 1 because the lock key family with key equal 2 stores a pointer to the primary key with key equal 1. Assume at the commit stage only key equal 1 was deleted due to an error, and there was no time to delete key equal 2. After recovery, when key equal 1 is read, it is found that there is a lock in the lock column family pointing to key equal 1, and the actual lock corresponding to key equal 1 has been deleted. We know that there was no time to delete the lock with key equal 2 before the error. This means that the transaction was actually committed successfully. As a result, the problem of distributed transactions mentioned previously was solved. We have only briefly introduced the Percolator model here. The actual implementation is more complicated, and we have omitted some details. If you want to know more about it, you can refer to the Distributed Transaction course. From the implementation of distributed transactions, we have learned that if a row of data is involved in a transaction and it is uncommitted, then reading it returns an error. Another way to say this is that writes not only block writes, writes block reads too. In theory, this is not a problem for systems with high concurrency. If a row of data is involved in a transaction, then the operation on that row of data will immediately become serial, which is very inefficient. The solution to this problem is called Multi-Version Concurrency Control, MVCC for short. Let's take a look at how TiKV uses MVCC. In MVCC technology, whenever you want to change or delete a data object, the database does not delete or modify the existing data object. Instead, it creates a new version of the data object. In this way, concurrent read operations can still read the old version of data, and write operations can be performed at the same time. The advantage of this mode is that reads are no longer blocked. In fact, there's no need for a lock at all. In the distributed transaction section, we saw that TiKV actually only adds put and deletes to modify or delete data instead of modify or deleting the original data. So in TiKV, we have data from previous versions. So the next question is how to find the right version of the data. Let's assume a scenario. There are currently two transactions. Transaction 1 has committed with a start timestamp or start underscore TS of 100 and a commit underscore TS of 110. Transaction 2 is started but is not yet committed, and its start timestamp is 115. When the timestamp oracle is 120, we query the values of key equal 1, key equal 2, and key equal 4. According to common sense, if there's no MVCC mechanism, then key equal 1 and key equal 4 will return an error or be blocked because they are our uncommitted transaction number 2. We can query the updated key equal 2 whose value is candy because transaction 1 was completed. However, if there's MVCC mechanisms involved, we know that we can read with a timestamp oracle of 120. In this case, we would get key equal 1 value equals Jack, key equal 2 value equal candy, because we are reading the committed transaction 1. On our diagram, we can see the three column families in the RocksDB instance in a TiKV store: default, lock, and write. On the far right of the diagram, you see the write column family. Since only transaction 1 is committed, there will be a record of transaction 1. The commit record with two values, key equals 1 and key equal 2, and the value change is start underscore TS equals 100. There's also a key equals 4, and we see that this start underscore TS is 80, so this record was submitted before. On the far left, we have the default column family. There are key equals 1, key equals 2, and key equals 4, where the start underscore key for key equal 1 and key equal 2 is 100. That is, the two lines of transaction 1 commit in write column family, and the start TS is for key 4 is 80. In the middle, we have a lock column family. Since transaction 1 has already been committed, locks with key equal 1 and key equal 2 in transaction 1 are deleted. Since transaction 2 is not committed, locks with key equal 1 and key equal 4 in transaction 2 still exist. So, in what order are these data stored in RocksDB? Let's pay attention to the following points. For every column family, the key is user key plus start underscore TS or start timestamp. For the write column family, the key is user key plus commit timestamp. And for the lock column family, the key is user key. Note, the user key here is the business key, and the key refers to the key stored in RocksDB. All column families are stored in the order of user key. Second, the same user key is stored in start_timestamp or commit_timestamp order from most recent to the oldest. This information will help us understand just how MVCC works. So, how does the MVCC mechanism work? When the TSO is 120, that is start_TS equal 120, we start a query with the values of key equal 1, key equal 2, and key equal 4. First, we have 2 pointers to scan in the write and lock column families. In the write column family, we scan key equal 1_110, the user key equals 1, and the committed timestamp oracle is 110. And in the lock column family, we also see key equals 1. This lock is obviously an uncommitted transaction. Yes, we ignored it. Since the values that have been committed are recorded in the write column family and are based on time from the most recent to the least recent, key equals 1_110 in the write column family is the most recent commit with a TSO of 120. So we follow key equals 1_110, value equals 100 in the column family, in the write column family. And in the default column family, we see key equals 1_100, value equals Jack. Next, we continue to read in the write column family. Scan key equal 2_110. That is, user key equals 2 and the TSO submitted is 110. And we did not find key equals 2 in the lock column family. Remember, our TSO is 120 at this point. The value that was submitted is recorded in the write column family, and it is more recent. Therefore, in the write column family, key equals 2_110 is the most recent commit. So the data for key equal 2 is value 100 in the default column family. That's what's returned. Finally, and key equals 4 is found in the lock column family. This indicates that user key equal 4 is in a transaction, and in the default column family, key equals 4_150. The next value is key equal 4_180. Since 80 is more recent than 120, the committed value is Tony.